Okay. So before we wrap up with kinematics, this is going to be the last lecture on kinematics before we start kinetics. A few more words about intrinsic coordinates. So if you recall, we defined this coordinate system created by first vector, which is the direction of the velocity of a particle with respect to a given reference frame A. So we had a particle P here, its velocity V in A. And so we defined the tangent vector like this. We said the first unit normal is d et in A dt over its norm. And please correct your notes in case you haven't done it. At the end, we realized I had it swapped. So the definition of this, the unit binormal is et cross en, not the opposite. I think at the beginning I gave you en cross et, and then we corrected it. So as I said, these are used for practical purposes. I wanted to just mention a couple of things that are interesting, and I really don't want to spend too much time on them. But the plane ET-En, it's called, I think it's called oscillating plane, if I remember correctly. And in particular, of course, the ET vector, it's obvious, it's the direction of motion, the velocity vector. The first normal here, in this point, for example, of the trajectory, will point, well, of course, I picked a flex point, but let's say that you are up here. Just a generic point here. The normal will always, the first normal will always point towards the center of what is called the oscillating circle, which is an imaginary circle which is tangent to the trajectory in P, and whose radius is going to basically give you how sharp of a curve the trajectory is in that location. So, of course, if you have something that looks like this, and you're up here with your P, the circle here will be smaller. And there is a parameter-defined curvature, which is, I believe, the opposite, the 1 over r or something like this, proportional to this, that is telling you how sharp is this, the trajectory in this particular point P. And this is extremely useful because it will tell you, again, if this is a roller coaster, what are the accelerations that people are going to experience up there? And they're going to be higher and higher as the curvature increases, of course. So these are coordinates that have very important uses, not only to project forces for an airplane, etc., also to tell you in which direction the curvature is going and how sharp that is. So it's basically they carry important information about the trajectory itself, but we're not going to see curvature and all these things. But I thought I would complete the conversation about these coordinates with these few remarks. And again, this is the right definition for EB. Okay, so what we're going to do today in one single lecture is real quick derive a couple of properties for rigid bodies. So we're going to see kinematics of rigid bodies. Do we remember the definition of rigid body? Or reference frame? They're the same thing, remember? As far as we are concerned, they are the same thing. In some cases, they may have a mass, in other cases, may not. We don't care for now. What is the definition of reference frame / rigid body? This is the very first time we met. What is the definition of, how do you define a reference frame?
Any 3 non-collinear points.
Okay. That was almost complete. What do they need to do? These points is any set of at least 3 non-collinear points. Right. Whose mutual distances constant, right? And that is good enough for a rigid body as well. You may see definitions where rigid bodies are given as the limit for the number of points that goes to infinity and the mass remains constant, stuff like that. I mean, a continuous body, it's fine, it's a rigid body, but I don't care if there are infinite points, as long as there are 3 that are non-collinear and the mutual distances remain constant, that's a good rigid body. So that is really what we're going to use. And so there are some properties for rigid bodies that we're going to derive, 2 properties in particular, that can be very useful. As you can imagine, if you know position and velocity of a point on a rigid body, and you know its rotation rate, the angular velocity, you should be able to tell everything about any point on that rigid body. That makes sense, right? In 6 degrees of freedom, in 3D Euclidean space, a rigid body should really need 6 parameters to be completely determined in its position and orientation. And so if I give you how a point on the body is moving and the rotation of the body, you should be able to tell me everything about any other point on the body. And we're going to demonstrate that real quick. So what I want to do is the following. Say that I am sitting in a reference frame A. The origin, of course, is fixed in A of this coordinate system here, all fixed in A. And I'm looking at some potato here, which is a rigid body. And then I focus on 2 points that are part of the rigid body, so they are fixed in R. And again, R is another reference frame as well. Point Q, point P. So we call the position of Q with respect to O, I'll just call it RQ, this vector. The vector from O to P, I'll call it RP, of course, and this is RQ with respect to P. I will derive the following quantity here, V of Q with respect to A minus V of P with respect to A, and the same thing for the accelerations. Because these are extremely useful expressions that will allow you, we'll see today also rolling, the definition of rolling, they will allow you to find velocities and accelerations of other points when you know something about, in this case, P. And P may be a very convenient point where the computation of velocity acceleration is straightforward. So, okay, what is this? What is VQ minus VP in A? What would you do? Look at what I gave you. I gave you a reference frame. I gave you another reference frame, right? And then I want velocities. Well, it's a difference, but they're still velocities of Q and P. The fact that there is an A here and it's a velocity, definitely there is a ddt in A somewhere, right? Of what? We've seen it. Remember when we went through the pain of deriving the huge formula with the Coriolis acceleration, centripetal acceleration, Euler acceleration, and then I told you, well, but forget about that. In a rigid body, we're basically redoing the same here, just formalizing it. In a rigid body, if you know the acceleration and velocity of a point, then you just have, for any other point, you just have to compute the velocity of that second point with respect to the first one, and the acceleration of that point, second point with respect to the first one. So this is what I'm doing here. I'm doing the velocity between Q and P, right? So it's the derivative of a vector. Which vector? RQ with respect to P, right? That's nothing special here, right? Makes sense. I mean, you can actually express it entirely. This is d dt in A of RQ, right? Minus, which is the first velocity, minus d dt in A of rp, but I can, given the properties of derivatives, I can just write these. And this is rq with respect to p. OK? Now, guess what I'm going to do? I'm going to use the transport theorem here. D dt, I have another frame here. I have r, the rigid body r. So d dt in r of the same vector, rq with respect to p, plus omega ra cross with rq. Let me actually write it like this. But these two vectors are the same. rq with respect to p or rq minus rp are the same thing. What do we observe here? What is this? 0, right? Those 2 points are part of the rigid body, so their mutual distance is constant. They don't change with respect to each other. So there is no rate of change as seen by an observer in R. If I'm sitting on the rigid body there, I don't see that RQP vector changing ever, right? Doesn't matter what R does. 0. And so this doesn't look that complicated, but I'm going to call it property number 1. This is only valid with a rigid body, right? So the difference between 2 points, in terms of velocity, between 2 points on the same rigid body is given by the angular velocity of the rigid body with respect to the chosen reference frame A, which is an arbitrary one, right? In this case, it's just a different reference frame from the bodies, 1, cross with this vector. So that's property number 1, if you like. OK, and we use it a lot. Second is, well, same, d dt in A. Now, what is the vector that I'm derivating here? Right? Which is this vector here. Another way to write this is v of q with respect to p, right? If you want to put it in a more compact way. But I would rather leave it like this because we use it in a problem. OK, so what do we do? D dt, what would you do here? Suggestions? I'm looking at this vector now. I have to take its rate of change in A. That's what I have to do. How would you do that? Omega r in A cross with rq minus rp. Remember, you have 2 reference frames involved here. You can guess. You can do whatever you want. This is not a test. This is just thinking together about these problems. What do you want to do?
The transport theorem?
Oh, I've done it before. I'll do the same. d dt with respect to r, vq with respect to p in A, plus omega ra cross with the same. So I'm actually going to write it entirely here. Fine. So this is what it is. Need to compute this one here. What is the rate of change of this cross product in R? Well, d dt in R of omega r with respect to A cross with rq minus rp plus omega ra cross with d dt in R rq minus rp. Do we agree on this? At this point, these things should not be an issue. If they are, you're not solving enough problems. You're not spending enough time on the book and problems, and you're not coming to see me at office hours. Does this make sense? So this is the vector up there that I'm computing the rate of change of with respect to R. So we've observed before this is a 0, right? d dt in R of this vector is 0, so this second term goes away, and that's what I'm left with. But what is this? We have said before this has a very clear definition. That's the angular acceleration that actually doesn't depend on which reference frame you use to do the derivative. So that's alpha r in A cross with RQ minus RP. Okay. So when I put all these together, I think I can erase these, and I want to write my properties up here. Let me move them so I don't need to erase them when I'm starting to do problems. So I have number one here, velocity of a generic point Q minus the velocity of a generic point P on the same rigid body as seen by an observer in A is omega of that rigid body with respect to A cross the vector from P to Q. Okay, that's number one. And number two, with the accelerations now, is AQ minus AP. The difference between the accelerations of these 2 points belonging to the same rigid body R as seen by an observer in A. This is given by this term down here, right? And this other one here. That's all we have. So this is alpha R A cross with RQ minus RP plus omega RA cross with omega RA cross with RQ minus RP. Okay. Are we all convinced about this? This is exploiting the fact that those 2 points have a constant mutual distance. The RQP vector does not change as seen by an observer in R. And if you go back to that day when we computed the big formula with the Coriolis accelerations, Euler accelerations, etc., this is the same with some simplifications. Now the point Q and P have a fixed distance. That's what they are. It's the same exact formula. In that case, we would move this point P on the right-hand side, and it was called the origin O of the frame that was rotating and translating. So the same for this, it would be on the right-hand side. But these, if you go back to the notes that you have for that day, and you start removing all terms so that you respect this condition that basically RQP is fixed with respect to an R, that's what you get. And you can call that point P as the origin of the coordinate system which is attached to the body R. So they're just a simplified version of those formulas, which you're more than welcome to remember or compute every time, which is what we've done here in 5 minutes, probably. Okay? But I need to know if this caused you any trouble. Doing this calculation, everything was clear? No issues? Because at this point, we really need to be able, this is a vector, by the way, to do this without any problems. Okay, so this is really what we need to, this is the kinematics of a rigid body. That's all we need to know. We know how to compute the velocity, the angular velocity at this point. With these formulas, we know how to relate the motion of 2 points. And again, in most of the problems, why do we care about using these expressions? Because this point P will always pretty much be a point whose velocity and acceleration is quite simple to calculate. And then once you know those two, and you definitely must know the angular velocity, and so its derivative, then you can just compute the right-hand side and tell me what happens to any other point Q on the rigid body. Okay. So the next thing that we're going to do is the following now. Rolling and sliding. I'm not going to do much about sliding. Sliding is just not rolling, pretty much. So these are 2 things that quite often are mistreated, especially rolling. Rolling happens between 2 rigid bodies, and we'll define it as a kinematic condition. Nothing else than this. It's a condition on velocities, and there is nothing else to say about rolling. There is one only definition about rolling between 2 rigid bodies, and that's the one that you need to use. Nothing else. Everything else that you can think of center of rotations, all the things that you've heard so far, you can throw them away. This is the only one that you apply and it always works because that's the right one. So if I'm giving you two rigid bodies, let's call them R and S. Of course, here there must be contact. Talking about contact between rigid bodies. There is no rolling or sliding if there is no contact. Okay? So these two bodies are in contact at point C. We probably have another reference frame which is not R or S. It's another reference frame A. So we have a coordinate system somewhere attached to that frame. So we call C the instantaneous point of contact. Instantaneous point of contact. Again, all we're going to discuss makes no sense if C doesn't exist, if the two bodies don't touch each other, of course. So one thing to understand is C is not a fixed point. It can move in all of these three reference frames. So at this particular instant in time, you can talk about the point C as belonging to R and the point S as belonging to, and the point C belonging to S, which are touching each other. But at the next instant in time, they can be different points. They can be two new C points in both bodies. So this C point can be seen moving from A. It can be seen moving, the point of contact can be seen moving in R and S. What I can tell you is that VC of that particular point in R is 0. So if imagine R is rolling, is changing configuration, and now the point of contact goes here, right? Here and here. So in the next time instant, these 2 points are touching each other. So C has moved somewhere else here. But it's still a point. I can still think about that point as being part of R. Same for S. But the contact is evolving, is changing. That point is changing. So that there's two different things going on here. There is a point of contact which is moving, and then there is the point which is part of R, and then the other point which is part of S, which at that particular time is the contact, but then it's a new one. Does this make sense? Okay. So if it doesn't, you should stop me. Rolling is defined as the following kinematic condition. The velocity of C on R as seen by an arbitrary observer in an arbitrary reference frame A is equal to the velocity of C on S as seen by the same observer. So what those two are is the following. VC. So I imagine the point C as part of R in this case. So this is the velocity of C on R as seen by an observer in A. And then likewise, this is the velocity of the point C on S, blah, blah, blah. Same story, seen by an observer fixed in A. So rolling is this. It doesn't matter from which reference frame you're looking at. Point C, the 2 points that correspond to the contact at that time, that particular instant in time, have the same velocity as seen by any other reference frame. Is this making sense? Can you imagine this rolling on the table? Right now, C is the point of contact here, but then the moment that this moves on, C is somewhere else. There is a new C down there. Okay? But if I am with this piece of chalk and it's rolling on the table, the C right now is not going to change with respect to an observer on the piece of chalk, but it can change with respect to an external reference frame. So this is really the only condition that you need to apply for rolling. If this happens, then you have rolling. Nothing else. There's nothing else you need to say. You focus on the point of contact and you establish if the velocity of that point as a point that belongs to the first rigid body and as a point that belongs to the second rigid body is the same, then you have rolling. If that doesn't happen, then you have sliding. That's a pretty simple definition. So sliding is, if you like, this is really the only definition I'm going to give you. It's not rolling. That's it. When this doesn't happen, then you have sliding. This is the moment where you may want to ask questions. I'm going to start solving a problem right now. Very simple one. The standard cylinder or circle that moves on a flat surface. Pretty standard stuff, but very important to understand how to use these basically 3 things that I gave you today. These 2 properties of rigid bodies and the condition of rolling. That's all we're going to use to solve a simple example. Does this make sense? Can we visualize all this? Okay. Okay, I don't need any of these. The definition, I think, is pretty simple to remember. So, as I said, pretty standard problem here. I have the ground down here, just a flat surface, and hopefully a circle. That's pretty close. Point of contact is C. Let's call this D disk. Center is O. And then I'm going to focus on a generic point P on the edge of the disk. We measure the position of this point P with respect to this direction CO with an angle theta, which is positive clockwise for us on this side of the board. And we call this radius R. And there is rolling, or as is sometimes indicated, this is rolling with no slip. Which I think is actually pretty redundant, but it's rolling. That's what it is. But you see it often that way. So I want velocity of O as seen by an observer to the ground, fixed to the ground, acceleration of O as seen by an observer fixed to the ground, and also the same quantities for P, that generic point up there. And we're going to use these 3 ingredients, these 2 properties, and the fact that I told you there is rolling. So I will build my way up from C to O to P to find these quantities. You have the information that there is rolling, so something is going on about C, and we use that right away. And then you have a rigid body here, the disk. And once you have what is happening to C as a point which belongs to the disk, then you can build your way up to O and P. I'm going to ask you a question right now. Well, let's actually first apply the rolling condition, and then I'll ask you that question. Okay, so if there is rolling, the point of contact is C, and we define the following reference frames. Let me do my diligence here. And not skip any steps. We have the ground. There is one rotation, so definitely I need another reference frame, and that's the disk. That's fine. And then I'm going to define my coordinate systems the following way. I'll do it this time a little more intelligently than what I've done in lecture 8, where I had, omegas that were negative, etc., which is perfectly fine. But in this case, I will make it a little easier. So if you do the following, you choose, so for the ground, you choose, let's see, EY along, origin at, allow me to choose O at time 0. I can do that, right? O will move, but at time 0 it's a fixed point, and it's there. Then I'll choose EY along OC. So it's pointing down, and note that OC is not going to change. And then I'm going to choose, for once, EZ into the page, because the rotation is clockwise. So if I choose EZ going into the page, then I think that my omega of the disk with respect to the ground is going to be a plus theta dot EZ rather than a minus. These are all things that you can, if you take more time, you can figure out at the beginning, and they may make your life easier. Again, if I choose EZ sticking out of the board, that is not a problem. You just have omega minus theta dot EZ. That's fine. It's perfectly fine. And then, since I tend to make these mistakes, and I have no problems repeating this diagram every time at the board, I'll define EX. That's the one I'm missing, right? Yeah, EX as EY cross with EZ. And that's your EX going this way. Fine. Can I erase all these? Well, I'll do it after I define the other one. Disk. Well, I guess origin at O is fine. The rotation, after all, is happening about an axis perpendicular to the board. So that point is good, and it's fixed in the disk. So ER along OP is little EZ is, well, let's reuse big EZ. And E theta, once again, let's do it right. The order is the following. What is E theta? EZ cross ER. OK. Fine. I've defined my reference frames and coordinate systems. So with this in mind, my rolling condition is the following. Actually, can you tell me what it is? And that is not my question for you. That will come afterwards. I have two rigid bodies here. One happens to be the ground, flat and nice. And the other one is a disk. So rolling tells me that the velocity of C, when C is seen as a point that is part of the ground, with respect to the ground, guess what? In this case, one of the two rigid bodies is also the reference frame that I pick to compute my velocities and accelerations. This needs to be equal to the velocity of C as part of the disk as seen by an observer fixed to the ground. Right? Make sense? So in this case, I happen to have, say, one of the two rigid bodies I gave you before, S, corresponding to A, which is fine. You pick which is the reference frame from which you want to observe the motion, and I told you to pick one of the two rigid bodies, just to make it easier. You can do that. OK. Well, what is this? What is the velocity of point C as a point which is part of G as seen by an observer fixed in G? What is it? You can tell whatever. So G is a rigid body, right? It's the floor. And this superscript, this superscript on the right indicates that I'm looking at the point as part of a rigid body. So is that point moving in G? If it's part of the rigid body, if this is a point on the here, and this is part of this table, is it moving with respect to the table?
No.
It's not. All the points in a rigid body have to have constant mutual distances. It doesn't go anywhere. So this is 0. It doesn't go anywhere with respect to an observer fixed in G. And so the velocity of C on the disk is 0. Nice to know. Now the question that I have for you, and I hope that I get to solve it, do you think the acceleration of C as, what do you think about the acceleration of C as part of the disk? What do you think that should be? Can you guess? And again, I don't like you to guess, but if you were allowed to guess for once, what would you say? Told you before, that point of contact changes. It's changing. Next time, this is rolling this way. So at some point, this disk will be up here. And this point C, as part of the disk, will be somewhere here. And there is another point of contact, right? Remember, I'm focusing on C as part of the disk now. So if in this particular instant in time, the velocity of C as part of the disk is 0, as seen by an observer fixed to the ground, can it stay at 0 all the time? If at some point during the rotation this point has gone up here, cannot be 0 all the time. So probably the acceleration of C as part of the disk as seen by an observer fixed to the ground, I know it's a lot of C, D, G, a lot of letters here, but it will probably not be 0. Because at that point in time, the velocity of C as part of the disk is 0. The next instant in time is not. Okay? Well, okay, I want the velocity of O. Let's start with O. Guess what? O is another point on the disk, which is a rigid body, and I already have the velocity of C. So I can do the following. I can say VO, be careful here, as seen by an observer fixed to the ground, because that's what I want. I don't need to put D here, because O only belongs to the disk. It's not a fixed point in the ground. So minus the other point now. So I'm looking at this formula here, where Q now becomes O and P becomes C. Well, velocity of C as part of the disk with respect to the ground. Now here I want to carry this because C can be also as a point fixed in the ground's reference frame. So, okay, so this is omega RA cross width. Okay, we agree that this is 0. Cross width, what is it? RO, right? Minus RC, which is equal to, and we said that this is 0. Okay, omega of, okay, now this is disk, I'm sorry. Disk, ground, let's be consistent, okay? I just changed the name of the reference frames. That angular velocity is theta dot big EZ. That's why picking EZ going in made a little bit of sense, but again, it's fine if you have it the other way. Cross width, what is RO minus RC? And you probably want to use the coordinate system with the big E's, because that's what I have already here. RO minus RC, remember that vector there was, this vector here was going from P to Q. So here I'm going from C to O. So it's minus R EY, right? And so this is giving me, what is EZ cross with EY is minus EX, so this is R theta dot EX. And this is actually the velocity of O with respect to the ground, because this term is 0. Agree? Disagree? You don't care? That's what it is. So I'll write it here. Can I? Yeah, no, I'll leave it there for a second.
Why is it negative?
It's not negative. Oh, this?
Yeah.
Okay, so this is the vector RO minus RC. And if you recall the initial sketch I had on the board,
Why isn't it right here?
is going from P to Q, right? So if you replace P with C and Q with O, this is a vector. This vector here is going from C to O. It's going up. It's this vector here, right? And so since my EY is pointing down, it's minus R EY. OK, so what is the acceleration of O, G? Do you think I need to use that? I mean, I can. They'll definitely get the same result. But I don't actually have the acceleration of C. I actually told you that I think it's not 0, but I haven't computed it yet. Look at this. What is the acceleration of O with respect to the ground? You have everything you need. And I know you may be thinking I must be doing something complicated. I have to do something complicated here with transport theorems, etc. Not always. Not always. This is expressed, the velocity of O with respect to the ground is already expressed in a coordinate system which is fixed to the ground. Nice. So sometimes you don't have to do anything. Not very often, but sometimes that's the case. OK? And that takes care of the first two. OK, I'm going to do the velocity of P now. So I want Vp in G. And I don't need to indicate that it's part of the disk because P is only part of the disk. OK, let's reuse that one. Minus.
It's just a linear velocity.
Yeah. What do you mean linear velocity?
The linear velocity of the linear acceleration.
Well, I don't know how theta is evolving with time, and this may be a weird sinusoidal function. The thing is rotating quicker and then slower and then quicker and slower. So yeah, it's always along Ex. That is true, but it's not constant. It may be theta may be changing.
Constant says that it makes sense that you're just multiplying the rotational by R, because the center is just, you're only seeing the.
In that particular instant in time, well, that's the thing. I told you I don't want to talk about centers of rotation, because if this wasn't a disk and it was an elliptical object or something else, that would not exist. But in this particular case, you could tell that C, you could probably say that C is the center of rotation. That's why you get that. But I don't want you to use those definitions that only apply to some cases. And if this was a full 3D problem, or you don't have a center of rotation. So, OK, so what I was going to do, velocity of P, well, I have C or I have O, for example. What do you want to do? Or do something else? I can do this, right? Let's use O. I've computed everything about O. So same expression. Omega dg cross with, what do I have now? Now I have Rp, be careful, Rp minus Ro, right? Correct? Angular velocities as before. Now probably, well, let me see if this makes sense. I'll write it in this form, but remember, little ez and big Ez are the same thing. Now, what is that vector? It's going, remember again, I'm going from O to P. O to P, given the other coordinate system, which I haven't really drawn here because it will be a little too much for that image. It will be, so I'm going from O to P, so it's R little er, right? So, you know, I can do this easily. I can transform Ez in the other basis just because it's little ez. So Ez cross with Er right there, E theta, so R theta dot E theta. Now you're more than welcome to add these two together and get your V of P. As I told you, this is fine. We're not doing kinetics yet. And unless there is a specific reason why you want to transform vectors to the same basis, you can leave it like this. So the velocity of P in G is the addition of these two terms, right? Done. You can stop right here, unless there is a specific reason why you want to transform those vectors. And then the acceleration of P, G, minus acceleration of O, G, well, that's the same. Alpha. What is alpha? Well, let me write it. Alpha dg cross Rp minus Ro plus omega dg cross with omega dg cross with Rp minus Ro. Let's substitute things here. What is alpha dg? It's theta double dot little z cross with Rp minus Ro. I just computed it somewhere here. It's RER, correct? Plus theta dot little z cross with theta dot little z cross with same R little er, which is going to give me Ez cross with Er is E theta, so I have R theta double dot E theta from the first cross product, and then I have theta dot Ez cross with what I get from here, which is Ez cross with Er, which is another E theta. So R theta dot E theta, which in the end is going to give me Ez cross with E theta minus Er. So in the end, I get this. R theta double dot E theta minus R theta dot squared. What did I say? I would get ER, right? ER. And again, you have A of O in G, which is this. So you only have to add this other term here, and you get the acceleration of P. And I'm fine if you leave it that way, unless you're doing something else that forces you to express big Ex into the other bases ER, E theta, Ez, or vice versa. So these are probably easier to remember than that particular problem, the general case, I mean, where we have Coriolis accelerations, etc. But again, you really need to be able to rederive them, applying the fact that distances between points in rigid bodies remain constant. Now, the question I had for you was the acceleration of this point as part of the disk seen by an observer fixed to the ground. We know already this cannot be 0. It needs to change. That disk is rolling. So if C is here and you think about C as part of the disk, some other time in the future, and this is rolling this way, it's going to be up here. So this point C, as part of the disk, has moved. It cannot remain at 0 velocity at all times, because that would be a hinge. If this thing doesn't move, this point doesn't move, it's hinged right here with respect to this is the ground. So if its acceleration is also 0 at all times with respect to the ground, that's a hinge. And people tend to think about rolling as hinges sometimes. This is a physical condition, while rolling is a kinematical condition. You only have to write that the velocity of C as part of G and disk, as seen by any other reference frame, is the same. That's the only thing you need to define for rolling, nothing else. There is no physical implications here, only kinematical, only velocity relationships. OK, so we know that probably we shouldn't get a 0. How do I find this point, the acceleration of this point? Well, I guess the same, I've done it before. I can reuse this formula here. I'll use point O. Why not? OK, let's try to plug things in. We have a minute. So that's theta double dot alpha. I'm substituting alpha RA is theta double dot, what do we say, little z? And then I have R, let's see, RC minus RO. What is that? RC minus RO. I'm going from O to C, REY. So probably I should do this. I have the luxury of switching between little e and big E. In this case, I can do it. plus theta dot. Well, let's stick with big Z. It's probably the most convenient thing to do. Cross with the same theta dot big Z cross with R EY, right? Let's do it. What is EZ cross with EY? You tell me. Can I go ahead? 1 minute? What is it?
EC plus EY is negative EX.
Okay. And that will go away with this once I bring this term on the right-hand side, right? So that will go away. And then you're left with this cross product. EZ cross with EY is the same as a minus EX, right? Theta dot. Minus EX. Okay.
Why are we opposite R EY to the negative?
Because it's the vector that goes from O to C. So it's pointing down now. Yep. Can you tell me what this is? What have I done here? There's something wrong here. I've done the first cross. Oh, this is a cross product. That's what it is. What is this? Is E cross with the X. Minus is plus EY? Plus, right? So this remains a minus. So in the end, I get minus R theta double dot big EX minus R theta dot squared EY. Is this okay? Remember that I erased that. Acceleration of O with respect to G was exactly this with a plus, so I bring it on this side, and this will go away. So in the end, except any error in signs here, which is possible since I'm rushing this is what you should get. So the acceleration of C as part of the disk is not 0. And that makes sense. Okay? We're done for today.